Okay, so the mobius function is multiplicative. So it's multiplicative. So mu as a function is multiplicative. Multiplicative. Well, therefore, I'm just going to write f of n equals sigma d divides n of mu of n. Mu of d, where mu equals the Mobius function. The Merb function. This f here, whatever it is, I don't know anything about it yet, but it is multiplicative. Let's just evaluate this. Let's work out f of, let's say, 12. Well, that's just writing out the definition. Sigma over d divides 12 of the Mobius function of d. Okay, well that's what it is by definition. Equals mu of 1 plus mu of 2 plus mu of 3 plus mu of 4 plus mu of 6, 5 doesn't go into 12, plus mu of 12. Well, I can cross some of these out straight away, because this one, 12 goes into 4. 4 divides 12, doesn't it? And 4's a square, so we can bin that one. We can bin that, of course. What else have we got? Mu of 1 equals 1 by definition. Mu of 2 is minus 1 to the power 1, so that's minus 1. Plus minus 1 again. Mu of 6 equals 2 times 3, so it's minus 1 squared, so it's plus 1, and that's disappeared. So it's 1 minus 1 minus 1 plus 1 equals 0. F of 12, capital F of 12 equals 0. Let's have another look at it. F of, let's say, 14 equals the sum over d divides 14 this time of mu of d equals mu of 1, of course, plus mu of 2 plus mu of 7, I think, plus mu of 14 equals 1 plus minus 1, because it's prime, of course, minus 1 for 7, plus, and 14 is 2 7, so it's minus 1 squared, because it's got 2 factors, it's minus 1 to the power 2 plus 1 equals 0. We seem to be getting quite a lot of zeros. Well, as it turns out, sigma of, if f of n equals d divides n of the Mobius function of d equals 0 or 1, 0 if n equals 1, no, 0 if n is greater than 1, I'm sorry, and 1 if n equals 0. Okay, greater than or equal to 1. Made a muck of that, didn't I? Let's write that out again. Let's write that out again. It turns out that f of n equals 0 if n is greater than 1, and 1 if n equals 1. I'm going to prove that. Okay, well, you'll remember from the last screencast, all I need to do is figure out, find or evaluate f of p to the k, where p is prime, k where p is prime. Okay, well, let's have a look at that. F of p to the k, and then I can work out what this capital F function is for any number just by multiplying my different prime powers together, equals the sum over d divides p of k of mu of d. But because it's a prime power, the divisors are dead easy to write out. That's just mu of 1 plus mu of p plus mu of p squared plus mu of p cubed. You see, I'm going through all the d's that divide p to the power k. Plus blop 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 plus mu of p to the power k equals, well, mu of 1 is 1 by definition, plus minus 1 for this guy here, because it's got 1 factor, so it's minus 1 to the power 1. These are all zeros because they've got p squared. All these powers are higher than the first. All these powers are higher than 2. So it's 1 from this guy and minus 1 from that guy equals 0. Okay, unless I guess that k equals 0, If k equals 0, this argument doesn't really apply, in which case f of p to the power 0 equals, well, may as well write it out in full, sigma over d divides 1 of mu of d, because mu of 1, because the only number that divides 1 is 1, equals 1. QED. So now we've figured out that this capital F of n, we've proved this result because we've evaluated capital F we've evaluated f of p to the k equals 0 if p is prime and k is greater than 0. So if we wanted to work out what f of, let's say, p1 squared times p2 to the power 4 times p3 to the power 7 equals, well, that equals 0 because this equals f of p1 squared times f of p2 to the 4 times f of p3 to the 7 equals 0. So there it is, and I'll use that in the next screencast.